Hi, the talk is about a fast parallel batch dynamic data structure for the closest pair problem. My name is Icho. This is work done at MIT with Shangdi, Yan, and Julian. This is the outline of the talk. First, problem definition, then data structure, after that, our parallel algorithms, and in the end, experimental evaluations. Let me first define the problem. The static version of the closest pair problem is defined as, given the point data set in the metric space, we want to find its closest pair of points. The dynamic version of this problem maintains the closest pair while allowing single updates, such as insertions and deletions. The batch dynamic version of this problem maintains the closest pair, but allows the updates to come in batches. There are numerous applications for the problem. The closest pair is very well studied in computational geometry. It is used for collision detection, linear spanning tree, hierarchical spatial clustering, etc. For a dynamic closest pair, is motivated by modeling moving or changing objects and as the growing number of evolving data sets. So in a simulated scenario such as a video game or in real air traffic control, we can use the dynamic closest pair to model moving objects and objects that appears or objects that disappears, while maintaining the closest pair to monitor potential collisions. For parallel batch dynamic closest pair, compared with just dynamic closest pair, there are many advantages. So first, it's advantageous when there are a lot of updates because the running time can be improved even with processing the batch sequentially. And also the batch can be processed in parallel and utilize modern-day multicore machines. Here's our overall contribution. We design efficient parallel batch dynamic data structure for the closest pair. We implement the data structure and perform comprehensive experimental study. We also implement, parallelize, evaluate, and compare with 4 static closest pair algorithms. So we test our algorithms on 48 cores with hyperthreading. So we achieved up to 38 times self-relative speedup. In addition, when comparing with the static algorithms, we see that it is more advantageous to use the parallel batch dynamic algorithm for batch sizes of up to 20% of the data sets. Below in the plot, I shows a plot of throughput, meaning points processed per second for updates, as well as the batch size of the updates. We see that with a higher batch size, the throughput increases. Specifically, it can be as high as more than 1 million points per second. The dataset itself is also very large. It contains 300 million points. It's a dataset in 3D cosmology. Here's our theoretical model for parallel algorithms. We use a work and depth model where we use a directed acyclic graph to represent an algorithm. Each of the nodes in the graph represent an operation in the algorithm, and each of the directed edges represent a dependency. If 2 operations doesn't have dependency between them, it can be executed in parallel by a parallel scheduler. The work refers to the total number of operations in such an algorithm, and the depth refers to the length of the longest dependency chain. So when we design our parallel algorithms, we aim for work efficiency, meaning the total amount of work should be the same as the sequential algorithm. We also aim for polylogarithmic depths. In the table below, we summarize and compare the work bounds for previous work, the sequential dynamic closest pair data structure by Golin, Rabin, Schwartz, and Schmidt, as well as our work, which is a batch parallel dynamic closest pair data structure that takes batch size of M. So both of these data structures take ON spacing expectation. For construction, both of them take ON work expectation. So since we constructed in parallel, we also have polylogarithmic depths. For the sequential data structure for each update, it takes log n work in expectation. Suppose if we process m updates using the sequential data structure, it will take m log n work. For a parallel batch dynamic data structure, we actually take only m log n over m work, which is less. So we're faster even running sequentially. But since we run the data structure in parallel, we also have polylogarithmic depths. The queries both takes constant time. Next, I'm going to introduce the data structure. So let me start with a static algorithm, the famous Golin-Martius sieve algorithm for the closest pair. So given a bunch of points, we want to identify the closest pair highlighted in red. We take a sieve which filters out points that are sparse. So those points get filtered out. We see that the two top points got filtered out. The denser points which have closer points nearby got filtered to the next round. Then we use a smaller sieve. Again, we put them into the sieve and keep only the denser points. So we see that the closest pair trickles down to the later levels where we can find the closest pair with lower cost. For the dynamic closed pair by Golin, Rabin, Schwartz, and Schmidt, they used a data structure called sparse partition. So the fundamental idea is similar to the sieve idea. So they keep all of these sieves as well as all of these levels. For example, for a dynamic insertion, they throw in a point from the top, and while it trickles down, it also moves points around in between these levels. For a parallel batch dynamic closed pair, so we based our parallel version on the sequential dynamic closed pair. We also use the sparse partition data structure. And specifically, we use the parallel grid-based sparse partition. We also design our own parallel batch dynamic heap to do internal bookkeepings. So this is some more details for the sparse partition data structure. So the input data set is called S. So the sparse partition is a sequence of tuples, Si prime, with I being from 1 to L. So there are L different levels. And for each level, we have these two sets. Si for level I represents all the points of level I. So Si and Si prime represent only the sparse point of level I. The difference between these two sets are the denser points, and they trickle down to the next level. Let's see examples on the right. The larger circle represents S1. We have these 2 points being S1 prime, and the red highlighted region denotes the denser points, which is going to be processed in the next level. So it becomes S2. In S2, similarly, we can still identify denser regions and also have 4 sparse points, and the denser points goes to the next level, becomes S3. And in S3, all of these points becomes sparse. This is a randomized data structure where how coarse or how fine the sieve is determined by a random pair of closest pair, which is randomly chosen. So therefore, there will be expectation log n different levels as well as overall linear expected space. And so in the program, we implement this sieve using the grid-based data structure. This is also done by previous work. So specifically, we impose an axis-aligned grid on the data points. So for 2D data, we have a 2D axis-aligned grid. For example, for each of these points here, we check its own box as well as the box neighborhood. So if the entire neighborhood, and including the box in the center, only contain the point itself, is considered to be a sparse point. On the other hand, so for this point, it has someone else in its neighborhood, so it's not considered sparse, but dense. So the sparse points are retained by the sieve, while the denser points got trickled down. In the example, we can see that actually the 2 sparse points are actually closer together than the 2 denser points. So this tells us that it's not sufficient to just find the closest pair in the last level. We have to do some bookkeepings to keep the closest pair in the dynamic data structure. Specifically, we use the heaps to maintain the closest pair. And remember earlier we talked about that for each of these levels, we have a sparse set, which is the white region. So the white region contains the sparse points represented by hollow blue circles. So for each of these sparse points, we find the restricted distance. So it is defined as the closest pair, its closest sparse points in its own level as well as k level before, where k is the dimensionality. For example, for this point here, its closest pair is simply in the same level. So this pair gives rise to its restricted distance. Whereas for this point in S2 prime, its closest sparse point is actually in the previous level. So this pair give rise to this point's restricted distance. For each of the sparse pairs, so we'd keep those sparse pairs in a main heap keyed by the restricted distance. And for the closest pair, we can simply read the last k heaps at the top of the last k heaps and take the minimum among the k values, where k is the dimensionality, which is a constant. And from that, we obtain a closest pair. So I have introduced the data structure used in both previous work and our work, next our parallel algorithms. First, we construct this sparse partition data structure. So overall, we make careful parallel primitives. We use parallel dictionary to represent the grid in both theory and practice. We also design our own parallel batch dynamic heap for the bookkeeping, as I have talked about earlier. The heap by itself might be of independent interest, so we include more details in our paper. And for the construction, we start with S1, and we first construct a grid data structure using the dictionary in parallel for all the points in S1. And for each of the points independently, we check its sparsity. So specifically, so these 2 points are sparse. And for the sparse point, again, independently in parallel, we compute its restricted distance, after which we use a batch insertion into our parallel batch dynamic heap. And the denser region of these points gets processed again in the next level. So the process is similar, so I'm going to skip that. So here's an example of a parallel batch insertion. So here I used a simplified example of consisting only 2 levels. As we can see that the data structure contains A, B, C, D, E, 5 points, where A, B, E are sparse and C, D are dense. So C, D are also present in grid S2, but in this example, they are both sparse in S2. We want to insert points F and G in parallel. Suppose this is where their coordinates are. We see that when point F are inserted, it converts A and E into non-sparse points, meaning A and E shouldn't be here, they should go to the next level. Similarly for F, because it's non-sparse, given all the points around, is also going to move to the next level. On the other hand, G is sparse because it has an empty neighborhood. So after insertion of S1, we move certain points to the next level. In this simplified example, all of these points will move to S2 as sparse, so we just stop here. And other than these grid updates, we also need to update the heap that we talked about earlier. So specifically, the heap maintains the restricted distance of these sparse points. Due to time limitations, I'm going to omit that. The deletion algorithm is similar, but just in the reverse direction. So as I have talked about earlier for this S2, right, the 3 points move as if they are new incoming points. This can cause a chain effect to cause more points to move to S3, S4, and so on. And one key theoretical challenge in our paper is to bound the total number of points moved when points are inserted in parallel because of the chain effect that we have just talked about. And the intuition is that a parallel insertion doesn't cause more points to move than inserting them sequentially. So for single updates, for the sequential sparse partition, our previous work has proven that they only move for each insertion, for each update, they only move order of 1 points across all the levels. For parallel batch dynamic updates, we prove that given an update of size m, we only move order of n points across all different levels. This example gives intuition on one level of how this works, and this is the insertion example. So we have blue points being existing points, and the 3 red points are inserted. Suppose they're inserted sequentially. When this guy gets inserted, this blue point moves. When this one gets inserted, because this guy is no longer here, it has no effect, but it moves this point to the next level. When this guy gets inserted, it moves this point to the next level. And we can see that when all of these 3 points are inserted in parallel, still these 3 point changes, but no more points changes. Okay, so for multiple levels, more details on the paper. We also have practical challenges because we implement this theoretically efficient data structure where not aspect of the algorithm design are efficient actually in the practice. So previously, I mentioned that for each of the level, we have to keep a parallel heap. And with the insertion, we need to update all the heap for all the levels, which is not efficient. So we figured that we can just keep one heap for the closest pairs in one of the sets at a particular level to just obtain the closest pair just from that heap. So this reduced the work during the updates. In addition, one key subroutine of this algorithm is to check the sparsity of each of the points, which involving probing its box neighborhood. So as the dimensionality increases, the box neighborhood size increases exponentially. And so we use dynamic spatial trees to maintain only the non-empty neighborhood boxes for high dimensions, which speed up the sparsity determination process. Okay, next I'm going to talk about some experiments. And this is our experimental setup. We test on the AWS machines where there are 48 cores with two-way hyperthreading. The machine has 768 GBs of RAM. So we test on 11 different data sets of varying distributions, and some of the data sets are actually real data sets. So they have widely ranging sizes and dimensionalities. So we test the parallel scalability of our implementation of the parallel batch dynamic data structure. So in the plot on the y-axis, I showed throughput, meaning the points being processed per second. And on the x-axis, I showed batch size. For the two blue and red solid lines, I show the parallel throughput for the dynamic insertion and deletion respectively. And for the dotted lines, I show that of the sequence of the parallel algorithm running on just one thread. As we can see that as the batch size increases, we expose more parallelism, so there's a widening gap between these two sets of lines. So on 48 cores with hyperthreading, so we achieve up to 38.57 times self-relativity speedup, as well as 15.1 times on average. We also benchmarked the parallel updates versus static algorithms, and this slide is for the insertion. And I don't have time to go into details for these static algorithms, but they are represented using the colorful dotted lines here. So for the experimental setup, we start with 4 million points, and we want to insert a batch of varying sizes. For the dynamic algorithm, we simply just insert the batch into the data structure. But for the static algorithm, we have to recompute the closed pair for the initial 4 million points as well as the new batch. So as we can see here, the y-axis shows the time for the updates, and the x-axis shows the batch size. For a pretty wide range of batch sizes, our parallel batch dynamic algorithm is much faster than the fastest static algorithm. And the gap actually widens as the batch size even decreases. So we also did a similar experiments for deletions, but we just started with a bunch of points and remove one batch. And we observe a very similar trend. For a very wide range of batch sizes, it's much more advantageous to use our parallel batch dynamic data structure. So here concludes my talk. So we designed the work efficient low depth parallel batch dynamic data structure for the closest pair. We also perform a very comprehensive experimental evaluation. So we open source our code on the GitHub. So the code is parallel. It includes the parallel batch dynamic data structure implementation, as well as the 4 parallel static closest pair implementations. Please also check out full paper on archive. Thank you for your attention.